All right, this will be a short lesson on improper integrals. Now, what the heck is an improper integral? Well, that would be an integral where either one or both of the limits is infinity, or the function that you're integrating becomes undefined at one of the limits or anywhere in between. So let's take a look at some examples. How about the integral from 1 to infinity of 1 over x squared dx? Now, first of all, let's understand what this integral means. This integral means if you have the graph of 1 over x squared, like this, from 1 to infinity, then this integral will tell you the area between the graph and the x-axis. But the thing keeps going on forever, so you might think, well, isn't that area infinite? No, Musbro, it might be, but then it might not be. So we need to actually compute this, because sometimes you have a finite area and sometimes it's infinite. So when one of the limits is infinity or more, then what we do is we replace the infinity with a letter. Usually the lower limit I'll replace with the a, the upper limit I'll replace with the b, and then you take the limit as b approaches infinity. Because infinity is not a number, you can't treat it like a regular number. And then now, on this part right here, you compute it just like any other integral. You find the antiderivative. This is x to the negative 2, so you get negative x to the negative 1 from 1 to b. Factor out the constant. And then you got negative, plug in the top number, 1 over b, minus, plug in the bottom number, 1. And then remember, we're taking the limit as b approaches infinity. So as b approaches infinity, what happens to this? Since the degree of the bottom is bigger than the top, this goes to 0. And what are you left with? 1. So this area, although it might seem to, for some of you, like it goes on forever, it should be infinite, it's not. The area is exactly 1 square unit. Okay, let's take a look at another one. What about the integral from 1 to infinity of 1 over x dx? Now the graph is very similar to that. So you might say, oh, that area is going to be finite too, but we don't know, so let's figure it out. So I'm going to replace the infinity with a b here, and then take the limit as b approaches infinity. Compute this integral normally. So what would that be? Natural log absolute value of x from 1 to b. So you're going to get natural log b, b is positive because b is approaching infinity, minus natural log 1, which of course is 0, so you get natural log b. So what would happen if you take the limit as b approaches infinity of this? This is one of our limits we had in the beginning. It's infinity! Right? Because look at the graph. What does the graph of natural log look like? It keeps on going up and up. It goes to infinity very slowly, but the limit is infinity. So what does that mean? That means this integral diverges to infinity. In other words, that's an infinite area. So it's kind of befuddling for some of you. How can it be for this one, it's a finite area, but for that one, it's infinite? Well, that's because this one gets closer and closer to the x-axis fast enough for that to converge, whereas this one doesn't. Okay, let's take a look at another one. Let's say something like this. What about the integral from 0 to 1 of 1 over the square root of x dx? Now, why is this an improper integral? Because at 0, this function becomes undefined. In fact, if we draw the graph, there's a vertical asymptote at x equals 0, right? It's like this. You know what? Let's make cube root of x. Makes it more interesting there. So from 0 to 1, let's say this is 1 here, we're talking about this area, but this graph is it's going up infinitely, and then it's getting closer and closer to the y-axis because that's a vertical asymptote. So that's why this is an improper integral, because of this. So what we do is we replace this with a letter. I'm going to use a for the lower limit, and then take the limit as a approaches 0. This is how you handle improper integrals. So this part here, you compute like you normally do. So this is the same thing as x to the negative 1/3. So the antiderivative is x to the 2/3, 3/2. From a to 1, factor out the constant. So that's going to be 3/2, plug in the top number 1, plug in the bottom number a to the 2/3. And then now we take the limit as a approaches 0. And as a approaches 0, what happens to this? That goes to 0. Therefore, the whole thing gets closer and closer to 3/2. So this area right there is exactly 3/2 square units. So that's an insight into improper integrals, and then we can do some really neat things with this. So here, let's take a look at this problem right here. Yeah, let's take again, let's look at the graph of y equal 1 over x from 1 to infinity, this area here. Well, we already computed it, right? It diverges to infinity, right? It's an infinite area. But what would happen now if I took this area and revolved it about the x-axis? You would get this infinitely long golf tee. What would the volume of that be? How do I figure out that volume? Well, we know how to do that. Drawing a rectangle of infinitesimal width. If that rectangle gets revolved about the x-axis, you get a disk. Okay? So what's the formula for the disk? Pi times the radius squared dx. And the radius is simply the length of that rectangle, so top minus bottom. 1 over x minus 0. And then you add up all of these disks from 1 to infinity. So, since the infinity makes it improper, replace it with the letter, take the limit as b approaches infinity. In fact, you want to throw out the pi? Yeah, why don't we just take this pi and throw it out here. Now, why don't we compute this integral here like we normally do, and that's the same thing as x to the negative 2, so you get negative x to the negative 1. Let's throw the pi back in. From 1 to b, factor out the constant, so you get negative pi 1 over b minus 1. And then now we take the limit as b approaches infinity. And of course, that, like before, goes to 0 because the degree of the bottom is bigger than the top. And then what do we got? We got pi. So what we did, isn't this kind of puzzling? You start with an infinite area, but then if you revolve it about the x-axis, you get a finite volume. The volume is pi cubic units. Whoa! And here's something even more puzzling. What would happen if I just take... You know what? I'm going to save this for a quiz or test. I'll just tell you about it. Anyway, what would happen if you just took this part of the graph from 1 to infinity, not a region now, and you revolve it about the x-axis? What is the surface area of that surface? Is it infinite or is it finite? Well, I will leave that to you to think about for a while. You can actually try and compute it on your own. So this lesson is pretty easy. It's pretty easy. So I think that's all you need so that you can do the problems. Good. Bye.